Dear classmates, welcome to the VLSI testing class. In this chapter, we are going to introduce the concept of diagnosis and the physical failure analysis. As you can see on this cross-road map, diagnosis is the last, but definitely not the least, in the EDA topics. Here is one motivating problem. Suppose we tested one chip on the tester. For the good circuit, the output of pin 7 is supposed to be 1101. But this particular chip produces all zero output. And your manager wants you to figure out what is wrong with this circuit under diagnosis or CUD. What should you do? So why am I learning this chapter? Diagnosis is a very useful concept which helps to find the fault or defect in the circuit under diagnosis, and it also helps to improve the yield. Here is one interesting quotation for this chapter. In diagnosis, think of the easy first. This quotation described the most basic assumption of our IC diagnosis. In this chapter, we will first do an introduction, followed by logic diagnosis, and we will talk about scan chain diagnosis. Then we will introduce some basic physical failure analysis. Then we will conclude this chapter. This figure shows the life stage of a chip. Once the design is done, it will be verified. If there is any bug, we will need to perform a debug for the RTL code or the physical design. After this design is thoroughly verified, we will fabricate this chip, and then we will perform silicon debugging on a small number of prototype chips. If there is no problem, then we will enter mass production. In production tests, those good chips are sent to the customers, and the failing chips are sent to diagnosis. Also, if there is any chip returned by the customer, we will also diagnose them. When the diagnosis is done, we will open the chip and perform physical failure analysis and take pictures of the defect and figure out their root causes. This information are then fed back to the designer, test engineer, or fabrication to improve the yield. As you can see in this figure, those red parts are related to diagnosis. So diagnoses are definitely very important in the life cycle of a chip. In this class, we will use the following definition. First of all, verification is done to check if a design conforms to its specifications. This is done before the chip verification. Debugging assumes that a design is wrong, so we will need to identify design errors that cause the failure. Before the chip fabrication, we will need RTL debugging. After the chip is fabricated, we will need to perform post-silicon debug. Diagnosis assumes that a design is correct, but it has manufacturer defect that cause failure in the physical chip. We have two different approaches. One is software diagnosis. In software diagnosis, we do not actually open the IC package. We use software to identify the fault. On the other hand, hardware diagnosis actually open the package and use hardware equipment to help us to find the defect. In this class, we focus on software diagnosis. Finally, physical failure analysis, or PFA, means that we actually open the IC package. We locate and examine the root cause of the defect. We take picture and then feedback this information to design, fabrication, and testing. Please note that different companies or textbooks may use different names from our class. Here is a real-world case. Suppose that in QA testing, we found some chip that failed only at 0 degrees C testing, but they passed room temperature and hot temperature testing. The yield loss is about 60 dpm, which is only 60 out of 1 million chips. This is a pretty small yield loss. So, if you are the manager of this chip, what would you do? Option A, sell this chip anyway, because no one would start a chip at 0 degrees C. Option number 2, throw them away since the number is pretty small. Or you have any other better choice? This is actually a real-world case that was published in 1998. The company performed a diagnosis and they found that the defect was actually caused by silicide open. Silicide is a thin layer of conducting material on top of polysilicon. At lower temperature, the defect resistance would be higher, so they cause larger delay fall than in room temperature. So this is a real-world case that they fixed the silicide in annealing process, and they also add cold temperature testing in production test to improve the quality of the IC. This case shows the importance of diagnosis in the real world. So why do we need diagnosis? First of all, we want to improve our yield. As we have shown in the real-world case, diagnosis helps to fix design or fabrication problems. In the case of memory, we can even fix the broken parts with redundancy. Number 2 reason, we want to assure the quality of our IC so we do not sell bad chips to our customers. Number 3 reason, we want to shorten the time to market because diagnosis can identify the obstacle to volume production. Number 4 reason, we want to make physical failure analysis easier. All of the above makes our boss happy. Diagnosis has become one of the key issues in modern technology. In ITRS 2005 roadmap, it shows that test for yield learning has become one of the top difficult challenges. So how do we perform diagnosis? This slide shows a typical diagnosis flow. We test the circuit on the tester. If the chip failed the test, we would obtain a failure log. For example, for this circuit, when we apply input 011, the good output should be 1. However, the chip failed this particular test. So we will send this information to our diagnosis software. On the other hand, we run fault simulation on this circuit to generate output of 40 circuit. With fault 1, we will get this 2 failing output. With fault 2, we will get this failing output, and etc. This fault simulation is a very time-consuming job, and then we would generate a fault dictionary. Diagnosis software take this dictionary and compare them so that we can diagnose fault 3 is the most likely fault. This is a general concept for diagnosis. So what is a good diagnosis? First, the diagnosis must be correct, so that real defect is contained in our diagnosed fault list. Sometimes wrong diagnosis is even worse than no diagnosis. Second, the ranking must be high. That means the actual defect must be within, say, top 5 of the diagnosed fault list. Third, a good diagnosis should have very few faults in the diagnosed fault list, and eventually, good diagnosis software should run very fast and requires very small storage space. Sometimes these requirements are conflicting, so we cannot meet them all at the same time. So what are the assumptions of diagnosis? We assume that a design is correct. So we diagnose manufacturing defects, not design errors. Number 2, we assume that less fault is more likely. Single fault is more likely than double fault. But please do anticipate multiple faults in the real world. The third assumption is that real defect behavior is hard to model. So far, we have introduced many fault models such as single stopgap fault and transition delay fault. Please note that they are not accurate for diagnosis all the time. But hopefully, we can find a defect very close to our diagnosis fault. In summary, for diagnosis, we need to note that fault models are not 100% accurate. This slide shows basic terminology that we will use in this chapter. A failing pattern is a test pattern where CUD output differ from good output. For example, suppose that we apply 4 patterns to this particular circuit. We have observed 2 failing patterns where the faulty output and the good outputs are not the same. So the failing patterns are number 1 and number 2. A failing output of a failing pattern is a pin whose output differs from good output. For example, in this particular case, the failing output pin is output number 8. Test failure, or TF, is sometimes known as failure log. Test failure means the failing pattern and the failing pin information of a defective CUD. This is observed on the tester. On the other hand, simulation failures, or SF, are those failing patterns and failing pins of a particular fault which is obtained from fault simulation. Because the behavior of real defect is not the same as a full model. So in diagnosis, please don't expect that test failure will be completely the same as the simulation failure. A complete fault dictionary contains all the faults and their simulation failure. And the partial fault dictionary contains a subset of faults and their simulation failures. For you to remember this terminology easier, we will use the following analogy. Test failures are like patient symptoms, and simulation failures are like symptoms of a particular disease. A complete fault dictionary is like a full collection of symptoms of all disease. So this is a very large information. On the contrary, partial fault dictionary is a partial collection of symptoms of some selected disease. So this is a relatively small piece of information. We can classify diagnosis techniques into several categories. In the first category, we call it static cause-effect diagnosis. In this technique, we pre-compute simulation failures for all the faults, and we store this information into a complete fault dictionary. And then we compare this complete fault dictionary with test failure to perform diagnosis. In analogy, this diagnosis technique is like an intern doctor without any experience. So he is trying to look up patient's symptoms in a general pathology book, which is a large amount of information. The second technique is called dynamic cause-effect diagnosis. This diagnosis is smarter. Based on the test failures, this diagnosis will simulate only a subset of faults, and we only need a partial fault dictionary. The concept of dynamic cause-effect diagnosis is shown in this figure. We feed the test failure to the simulator, so we only fault simulate a small subset of faults to generate a partial fault dictionary. In analogy, this diagnosis technique is like a doctor with some experience. So he looks up patient symptoms in a specialized pathology book. For example, if you had a headache, then he will look up the book in the neural system, not the digestion system. The final diagnosis technique is effect cause diagnosis. Based on the test failure, this diagnosis do not need any dictionary. It will do logic reasoning to figure out the fault. As is shown in this figure, this diagnosis technique does not any fault dictionary. In analogy, this is like a very experienced doctor with no textbook at all. In summary, what is diagnosis? We want to identify the most likely fault or faults to explain test failure of a particular circuit under diagnosis. And what is good diagnosis? We want it to be correct and high ranking, and the diagnosis result should be very good in resolution. So how can we diagnose a chip? We can use static cause effect, dynamic cause effect, or effect cause diagnosis. This is the end of this video. Thank you for watching.